Right. Is that for a second? There's no way to make that smoother to switch from having the splash screen up to actually doing the recording. You just gotta
Just commit.
Yeah, yeah, absolutely. Great star party last night. That
I
was really
thought so.
It was really good. We were in a silly mood, which is always important.
Isn't that always true as
I
well?
I think we could say that every episode of the virtual star party has a little bit of silliness in it. But there's some great objects, and the stupid moon, which we looked beautiful, but also
I'm not sure
was,
that the moon actually has an intelligence quotient.
I wonder if we can destroy it. Can we destroy the moon? Because that would really help our astronomy. Yeah.
I think it would actually be rather bad for the surface of our planet.
But good for astronomy. So, and maybe if you gather together astronomers and put together a fund and see if we can destroy the moon. Why walk on the moon when you can destroy it? So, all right. So, for anyone who doesn't know what's going on here, it looks like the silliness is clearly carried over from last night. So, we're going to be doing a live episode of Astronomy Cast. That's where we record our long-running podcast, where we're going to be discussing. Today's topic is the Oort Cloud. And I know I'm going to get some emails from people who can pronounce it properly. Oort Cloud. We're going to be recording the episode of the Oort Cloud, and then we're going to stick around for 15-20 minutes afterwards and answer any of your questions about space and astronomy. So we'll be getting that rolling right away. Now, did we have any announcements? I think the people who are watching this right now, just a reminder that we're going to be going to South by Southwest in Austin, Texas from March 7th till 11th, really the 8th, 9th, and 10th. And we're going to be hovering around the gigantic model of the James Webb Space Telescope, life-size models as big as a tennis court. And we're going to be doing virtual star parties, we're going to be doing a weekly space hangout, and we're going to be helping out with the telescopes and giving people a view to the night sky. So if you're going to be in the Austin area for South by Southwest, definitely look us up. Hopefully you'll recognize us there.
No bracelet required. Everyone is welcome at the NASA event.
Right, so you don't even need to pay any money to get into this stuff. Perfect. Yeah, because it's like $1,000 to go see the bands part. But
Yeah, I have no idea. So we're going to be there for South by Southwest Interactive.
yeah.
And we will be trapped in our tent down at Zilker Park, and we're going to be trapped by all the enthusiastic people who come to see us and come to learn science.
So definitely, if you recognize us, drop over, say hi, shake our hands. We'd be glad to see you, and glad to, we'll find you a telescope to look through if that's where we are. So otherwise, we'll all just gape in awe at this gigantic model of the James Webb Space Telescope.
We'll have iPads with CosmoQuest on them, so you will be able to do science.
Yep, we'll get you to do some science, and then inside the big tent, there's going to be a gigantic wall that's going to have I don't know what the plan is. They're going to have big space stuff on the wall.
We're doing presentations. I'm giving 2 presentations each day. They're going to have astronaut John Grunsfeld, Nobel laureate John Mather, a bunch of other amazing folks. Sunday night, they're going to be looking to break the world record for the number of people taking an astronomy lesson in the public at once. So yeah, lots of good things going down.
I wonder if there'll be a test at the end.
I don't know.
All right, cool. So are you ready to go? Are you ready to record?
I'm hoping. So this might be one of those more interesting episodes because there is a lag between the audio and video going on.
Are you seeing a lag from me or a lag?
It's caught up for you, but for a minute you had a 3-second lag between your audio and your video.
Okay.
We'll live.
Yeah.
We always do.
Yep. Yeah, it doesn't matter. It doesn't affect the recording, so just makes the YouTube video worse.
It looks more like the news reports where one person's in Afghanistan and it's going through satellite feeds.
Yeah. That's funny. Someone mentioned our
press record.
Are you ready to press record? Okay, all right.
You are frozen. You have stopped moving entirely. There we go. Now you're catching up.
Okay, I suspect it's your bandwidth.
Yeah.
Okay, all right. So have you pressed record yet? Ready? Are you there? Are you ready to press record?
I've pressed it. It's not doing anything.
There's your problem.
I'm here.
Okay, tell me when you...
But I have a whirly rainbow. Okay, now I'm recording. We're all good. We're recording.
Okay. There, and I pressed record too, and it's working just fine without a whirly rainbow. All right. Let me get my intro going here. Okay, here we go. Astronomy Cast, episode 292 for Monday, February 4th, 2013, the Oort Cloud. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest.org. Hey, Pamela, how you doing?
I'm doing well, Fraser. How are you doing?
Great. So I'm not sure if anyone's going to get this, but we're going to be at South by Southwest in Austin for the South by Southwest interactive exhibit with NASA, and we're going to be near the great big model of the James Webb Space Telescope from March 8th to the 10th. And so if you're going to be in Austin, by all means come by and say hi to us.
And we aren't going to be doing a meetup because our meetup is the NASA tent. So just come join us, no bracelet required, open and free to everyone.
Yeah, we'll be there for 3 straight days. By all means, come by, say hi, shake your hands. Yeah. Awesome. Okay, do we have any more announcements?
Don't think so.
No? Nothing interesting happening on CosmoQuest? Well, tons of interesting things happening on CosmoQuest, like completely rebuilding the forum and such. But yeah, technical things. Okay, great. Well, then let's get going with the show. So the very outer reaches of the solar system is a region of space known as the Oort Cloud, which may extend as far as a light year from the sun. We only know about the Oort Cloud because that's where the long period comets come from, randomly falling into the inner solar system from time to time. So, Pamela, this is a funny thing where we've got an object, a structure, a thing in space that we actually have never seen, right? We can only just sense, detect, we have to presume that it's there, but we actually can't see it.
And it's really annoying because there's so many different things that it might be affecting. There are people that hypothesize that this continuous shell of icy material and dust around our solar system creates reddening. There are people that say that perhaps it's impacting our ability to measure distances, that perhaps it's impacting how we observe the cosmic microwave background, and we don't know. So there's all these things that its presence may or may not be affecting, and that's kind of really super annoying.
I had no idea. That's really interesting. So you can imagine that it depending on what the composition is of the Oort Cloud, which we'll explain in a second, but now I'm just excited thinking about this, that it's actually distorting our view of the cosmos because it's this bubble. There could be this bubble around it. Okay, well then for anyone who doesn't know, let's go back again and actually talk about what is the Oort Cloud?
It's basically this 2-component glob of stuff. So to get scientific,
that was very scientific. Yeah.
there is considered to be for the Oort Cloud 2 components. One, the big sphere that everyone talks about, that is it's roughly a light year across, 0.8 light years to be more accurate, is its theoretical outer limit, and that's based on how far away can something be and still be gravitationally attached to our solar system. And it's considered to be the source of some of our longest period comets, and the things out in it are considered to be like building in small moon-sized chunks of ice. But because we can't observe these suckers, we really don't know what their limitations are. So this could be just a big brother to the Kuiper belt, in which case we have a bunch more of these little dwarf planets out there. It could be limited to smaller objects. We don't know. And then nested inside this big spheroid of material is what's called the Hill zone. These are a disk-like component to the Oort Cloud.
And so where did the Oort Cloud come from?
Well, it actually came from a variety of different places, depending on who and which theories that you adopt. Most likely it came from a combination of places, both from during the formation of our solar system. The outer parts of our solar system were mingling with the outer parts of other solar systems, and we stole what we could gravitationally. So some of the constituency of the Oort Cloud is probably stolen material from other solar systems.
Right. You can imagine if it's this cloud, a light year or 0.8 of a light year across, that's a pretty big bubble that surrounds the solar system. You can imagine these star systems, they're Oort clouds passing through each other and material jumping ship from one place to another. Yeah.
And so this is one of the more intriguing things is we probably have some stolen material, and occasionally this stolen material gets gravitationally bumped until it comes into our inner solar system where potentially we can sample it. So that's kind of cool to think about.
Oh, and I'm sorry, but I just had an idea. I mean, so the theory like I know that when we do meteorite samples in the solar system, we find, that all the meteorites tend to have the exact same formation date.
Right.
That they all formed, 4.6 billion years ago with the formation of the Earth and the Sun and all of that. But can you imagine if we found, as you said, a sample of one of these comets that had a different age?
And it's harder with ice to do that because really you're dealing with ammonia and frozen methane and carbon dioxide and carbon monoxide and all these frozen gases. So it's a bit more difficult to age date them, but you can look at the compositional ratios and say the composition of this object doesn't match anything else we've seen. Now the issue is comets have a huge variety. So we're still trying to figure out what exactly is within normal boundary parameters for a comet. But the more we explore the Kuiper belt, the more we'll understand what something that probably formed with our solar system should look like, so that in the future, as we look at these long period comets coming into our solar system, hopefully we'll be able to say which ones are native and which ones, well, are the explorers of other solar systems.
Okay, so we stole material from other solar systems.
So that's part of the source of the Oort Cloud.
Maybe, probably. Who knows? Yeah.
And then the rest likely came from what can best be described as the angry dance of Saturn, Jupiter, Uranus, and Neptune in the early days of the solar system. As Jupiter and Saturn passed through having resonant orbits, they basically flung material in all directions. Some of this material, roughly a quarter of it, got flung into the inner solar system. Roughly a quarter of it got flung out of the solar system entirely. But then probably about half of this material ended up getting sent into extremely elliptical orbits, orbits that, well, mirror what we see for the long period comets. But because of the nature of the interactions, once that stuff gets out there, because the material does spend the bulk of its time at its most distant points in its orbit. This is true of every orbiting object. It's the Kepler's equal area and equal time law, where when you're in close, you sweep out this very fast angle so that you can sweep out an equal area to the amount that you, when you're further out, sweep out in the same amount of time as you move much, much slower. Now, once the objects are out there, they have the potential to gravitationally interact with other stars, with dark molecular clouds, with all these different things that we see as our solar system passes through the galaxy. And all of these different interactions, even, well, Oort belt object on Oort belt object interaction. All of these different interactions can work to smooth out those orbits to make them more and more spherical, more and more circular over time to create this distributed spheroid of material.
Right, and I guess that was sort of leading into my question, which is that you can imagine if there is these interactions of the giant planets in our solar system, kicking all of these objects out into the outer solar system, you would think that they would all be on these parabolic orbits, or where they're going out and they're all going to come back in. This material just keeps doing these orbits like the comets do. But I can see that once they get out there, they have these interactions, and maybe interactions with other stars, and it just changes their orbits and three-body interactions, and eventually you get it being, whatever remained is a cloud, and everything else got the sun or.
And the things that are on parabolic and hyperbolic orbits, they might pass through the inner solar system once and then they're gone. And it's the elliptical ones, well, some of them remain as comets. Some of them did have circular orbits and then got disrupted again and became comets. But most of the stuff, the orbits relax over time and we end up with this nice spherical component. We theorize it seems to match all of the comets that we see coming in. They have to come from somewhere.
Right, and so we've got sort of a source, an idea of maybe the source of this cloud. Now, what about the discovery and the name? So where did that come from?
Well, the name comes from the person who finally got the theory listened to. This is one of those horrible examples of science that things get named after whoever has the most loud way of presenting the information. So back in 1932, Estonian astronomer Ernst Upik, I think I pronounced that one correctly, said
Estonians, please tell us. Yeah.
He theorized that all of these long period comets that are coming at us from all different directions. So unlike most of the things that we see in our solar system, their orbits aren't confined to the plane of our solar system. They don't come from the same place that we see asteroids coming from. Rather, they're coming from all directions, completely randomized. And the only way to get to this completely randomized origins is if you have this orbiting cloud at the outermost edge of our solar system. So he put forward this theory. And then in the 1950s, it was re-theorized a second time, rediscovered, if you will, by Jan Hendrik Oort. And it was a way to try and understand where, again, are all of these comets coming from, and trying to understand why it is that all of these comets have such unstable orbits that we see. So when you see these sun grazers, when you see these clearly parabolic and hyperbolic orbits, which means they come in once and they're gone forever, well, those clearly aren't things that, like the planets, are orbiting over and over and over. So where are they coming from that they can keep getting renewed? And the only way to solve this paradox was to create a reservoir of comet material in the outer solar system. So later in the 1950s, Oort made this postulation. Let's face it, the word Oort is much more fun to say than Upik. So Oort ended up getting his name associated with this cloud of material in the outer solar system.
So what about the Hills cloud then?
That again, as a theorist, came along, worked on postulating, well, how do we explain all the distributions of material? And since it's a mostly random but not entirely random distribution where there is this preference towards things being in the plane, that preference can get explained by a second component that overloads the plane of the Oort cloud.
But is it one of those situations where there's extra comets coming from that region, and then that would be explained by this gravitational balance
second component.
Yeah, to give you this Hills cloud. And so right. And then, I mean, but again, this is pretty tricky, right? Because there's no observable evidence for this cloud at all. But
the way to think of it is, I'm trying to figure out how to not do this with a terrible example. So if you're getting sprayed with water, you know there's going to be either a cloud or a hose involved. And depending on how you're getting sprayed with water, you can start to figure out what characteristics the source of the water must have. And so here we're seeing the outcome, the water falling on us. And so we have to put together the pieces of what must be some of the characteristics. Now, if you can detail how far away the water is coming from, you start to be able to place boundary conditions. And the comets, well, they're the frozen water that's falling on us that places the boundary conditions on the physics that helps us describe this unseen frozen water faucet in the sky.
So let's talk about the comets that are coming out of the Oort cloud, because that's what we do have that direct experience with. What kinds of comets do we get from this cloud?
Well, for the most point, they're long period comets, things like Hale-Bopp that have orbits that are measured not in lifetimes but in generations, the rise and fall of empires. These are 1,000-year periods in some cases. But then we also get a few interesting exceptions, like Halley's Comet, which through interactions that it had with Jupiter in the past, at least we think it was Jupiter in the past, its orbit got changed so that it's now a shorter period comet, but its crazy orientation indicates that, well, it's not one of the ones that originated in the Kuiper Belt.
So, with a Kuiper Belt object, we're going to be looking at like what kind of period? These are the short period comets. I mean, they're measured in dozens of years.
Tens of years, 100 years-ish. Right. It's that order of magnitude. But with the long period comets, you're looking at order of thousands of years.
Thousands and hundreds of thousands. So really every comet is completely unique. The first time you see one of these long period comets, you're never going to see it again.
And that's one of the frustrations. And one of the other frustrations is even the ones that how even the Oort Cloud objects that do start to dip their way into our solar system, they have such extremely long orbits that they may not spend very much time in an observable part of our solar system. So a lot of scientists think that the dwarf planet Sedna, it's about, we think, roughly 1,500 kilometers across. It comes in to just 75 astronomical units from the sun. And that's an extremely large distance. Compare that to the 35 to 45 of most of the objects that we're looking at. So
but I know
that's its
Sedna,
nearest approach.
right? And Sedna then goes out to like what, like 10,000, 1,000, yeah,
Goes out to
1,000 astronomical
1,000.
units, yeah, and takes 10,000 years or something to do this orbit. Like it's crazy.
Yeah.
Yeah.
So and then we have other objects with less beautiful names, where there's 2006 SQ372. It's a 100-kilometer cross object. We're able to find it because it came all the way into about 25 astronomical units. So that's inside the orbits of the outermost planets. And it then will go back out to 2,000 astronomical units.
By any other name, these would be comets. I mean, if they got closer in to the sun, they would.
But so would Pluto.
So would Pluto, true. Yeah, so would Enceladus. But they would grow a tail, and it would be, I mean, can you imagine if Sedna or one of these got within the, within like Mercury's distance or Venus's distance of the sun, it would grow a tail. It would be unbelievable. I mean, most comets are only, 10, 20 kilometers. They're small.
Yeah.
And so these would be the brightest objects, ever seen. They'd be unbelievable.
And that would be kind of cool.
Wouldn't it? Yeah.
But unfortunately, the bigger an object is, the more force is required to disrupt its orbit. So the likelihood that the big ones are going to get jostled enough to come in and pay us a visit is fairly low. But luckily, the small ones are fairly easy to jostle into a visit.
But the small ones are also really dangerous.
Yes. Tunguska experienced that back in the early 1900s out over Siberia, where like roughly 1,000 square miles of trees got damaged and or flattened, and windows shook for thousands of miles. It was a big event, and so we try to avoid getting too close to comets, but they're not something we can exactly move our planet out of the way of.
Yeah, I mean, we've talked about this a bit in past shows, that with the asteroids, you can predict sometimes 100 years in advance that an asteroid is in a dangerous orbit, and you can take that time to research it and study it and move a spacecraft out and try to use a gravity tractor, or paint it, or shoot it with nukes or whatever you're going to do. You've got time. And even with the short period comets, you've got time. But with the long period comets, you have months, and then pow.
If that, I mean, one of the unfortunate things is, because they do have such highly elliptical orbits, you basically are making a knife's edge pass through the solar system. So depending on unfortunate geometric circumstances, it could be that something comes in from behind the sun that we don't notice until it's making a pass basically out of the part of the sky that the sun is located in, straight at the planet Earth.
Yeah. That is the worst case scenario. I mean,
and that's essentially what happened with the small asteroid that blew up over Russia. Is it came out of the direction of the sun, and we just didn't have early warning, and thus $1 billion rubles worth of broken windows and other damage.
And I'm getting surprised how big that asteroid was compared to what, originally people were saying it was like 70 tons, and now it's like 7,000 tons.
Yeah, 7,000 tons.
Yeah, it's actually a pretty big rock. So, okay, cool. So now you actually started off at the beginning of the show. You were talking about how this cloud might actually be affecting our view of the universe. So can you talk about that a bit more?
Well,
you're freaking me out.
So it's probably only a few tens of Earth masses worth of material. So order of 50 to 100 Earth masses at most. But that material, in some cases, is a sphere of basically dust. So you have chunks of ice that are colliding with one another, that are letting off this fine-grained particle as they crash into one another. If you've ever seen the images of geysers coming off of Enceladus, there may be material like what you see coming off the geysers created through the collisions of these objects over the billions of years. Now, we don't know that for sure. It could be that they're just nice chunks of ice that, because they're so far apart from one another, collisions are so remarkably rare that it is a land of no dust. But we don't know. And if there is this fine-grained particulate out there, this dust, it could be acting to scatter the blue light that's trying to travel its way into our inner solar system, creating this reddening effect on everything that we see as we try and look beyond the edges of our solar system.
So, like, what impact would that reddening have on our science, on our understanding of the universe?
Well, it would mean that our understanding of the temperature of everything is just a little bit off. Not a lot, but there have been people that have tried to explain some of the effects in the cosmic microwave background as perhaps being caused by effects of the Oort cloud adding a little bit of polarity or removing a little bit of polarity. People are making guesses, trying to understand what could be possible, and we really don't know. And that's one of the awesome things and horrifying things at the exact same time.
I mean, for example, specifically, like with the cosmic microwave background radiation, the temperature changes that they're trying to detect are really minute. And so
now, the nice thing is this would be a constant effect, assuming, and this is another, it's a huge assumption, assuming that the Oort cloud has a perfectly smooth distribution. And people have taken the time to try and look at that, trying to see if they can find some sort of a variation at the largest scales that could be explained by thickness variations in the Oort cloud.
Like when you're looking through the Hills cloud, you're looking through like the plane of the ecliptic through the Oort cloud, maybe you're going to get a different reading.
Right. And so these are all things that people are trying to understand. With the data that we have so far, it hasn't been at high enough a resolution that we can actually make out any effects to polarimetry or reddening that could be explained exclusively with the Oort cloud being the cause.
Now, we've talked about how the Oort cloud is really invisible. So what would it take to actually get out there and observe objects?
A lot of time. It sounds like I'm being sarcastic, but we're talking about 0.8 light years distance. So the best we can really do is wait for object after object to do like Sedna has done and come for a visit, and over time build up the orbits of a small catalog of objects that they come to us rather than us going to them. That's the best we can do. So more power to folks like Mike Brown who are out there trying to discover the largest objects of the Kuiper belt and the nearest objects of the Oort cloud. I
remember, and this is just coming to me now, that there was someone had put together a mission concept to be able to actually get a spacecraft out into at least the near part of the Oort cloud and be able to start, and it would essentially be a space telescope sent out into the Oort cloud, and it would just be observing objects and maybe fly past one if it can find one. But it would take, as you said, 100 years to get out to a place where it could do some science.
And even more problematic than that is, well, first of all, you have light travel time, so that the signal is going to take months to get back to Earth if you do get a telescope out there. But you'd have to launch a really big telescope because the Oort cloud will be extraordinarily diffuse. This isn't Han Solo's asteroid belt. Even our own asteroid belt isn't Han Solo's asteroid belt. And we're talking about tens of Earth masses scattered over a sphere, an entire spherical area that is 0.8 light years across.
I mean, the kind of civilization that could study the Oort cloud would be the kind of civilization that could send spacecraft to other stars.
No, that's actually not true, because it's easier to see from outside our solar system than inside. So if there is an Oort cloud out there, we can detect things like this around other solar systems. So detecting an Oort cloud from outside the system, where you can get the distance such that everything's compacted down and you're looking through the thickness at the edges, just like looking at a nebula. You can't really see the nebula when you're inside it. If you want to see the planetary nebula, you fly away and you see this ring where you're looking through the most parts of it. So detecting an Oort cloud, you really want to be that other solar system not too far away.
So do we see any Oort clouds around other stars?
We have seen things that resemble the Oort cloud around other stars. And so this is where we continue to think that our understanding should be perfectly reasonable. Unfortunately, things like nailing down exactly what its mass is, exactly what its furthest limit, exactly what its inner limit, those sorts of details, we're not there. But in terms of, yes, this is a perfectly rational theory to explain the comets, to explain objects like Sedna, we're onto something. And we're onto something that's fairly typical to see throughout our galaxy.
That is awesome. Okay, well, thank you very much, Pamela.
My pleasure. All right. Okay. Don't go away. We're just saving. And I will now unbury you so that I can see you. So this is one of those things, if you're a first-time watcher, you may not know, is Fraser and I do not look at each other while we're doing this. I cover him with a window. He covers me with a window. We talk to our cameras so that you get better eye contact and so that we don't distract each other.
Yeah. Let me just finish my save here. Safe. Okay. Yeah. So the problem is that if I'm talking to Pamela, then I'm going to look down like this because that's where her window is, down below. So it's actually quite distracting to see Pamela talk, especially because she does all this hand stuff.
What can I say?
Yeah, that was great. That was a really good show. I like that. So a couple of questions here. So Jeff Borst says, how far off could the redshift view be from all this material obscuring the view? In other words, how far off could our estimated age of the universe be?
So the redshift won't be affected. This is because it's based on atomic lines. And so when we talk about scattering out the blue light, it means just literally you have the black body distribution. Let's remove a little bit out of the blue. So where the atomic lines show up, that won't be affected.
But you could, I mean, I know that the most precise calculations of the age of the universe are done with the WMAP probe, and it was looking at the slight temperature variations in the cosmic, right?
But what it was looking at was, so the size of the temperature variations won't change. This would be a constant offset as far as we know. And so what WMAP was looking at is what are the number of temperature variations that are this angular size, And by comparing those, by building up a histogram, you can measure the size of the acoustic oscillations, and using geometry and a lot of really complicated cosmology, you can use the size of these variations and the variation in the number of things that have those size variations to figure out the age.
So the Oort cloud would be polluting other calculations, just not the age of the universe.
Yes.
Right. Okay. Mike Matessa asks, how do we know how the Oort cloud interacts with the local interstellar cloud?
Just theory. You run it through a computer. You figure out how frequently do we get close enough to something that the gravitation from that something affects it.
But I should have brought this up, but there are theories that some of the great die-offs that happen on Earth, the big extinction events, happen because maybe the Earth's Oort cloud the solar system's Oort cloud got perturbed by another star, and that sent a cascade of comets into the inner solar system. Yeah, but
none of those are mainstream.
No, okay, all right.
Yeah, none of those are mainstream.
But like once every 65 million years or something, right?
So the idea that we get, there is for some reason this periodicity, but it's not like a wave front of comets comes in. That's roughly how often something happens that sends one thing in.
But if you did get a close interaction from a star, you would get a cascade of comet. Like you would get a lot of perturbations in the Oort cloud, right?
But we again don't know how many would be near enough on that side. Big empty thing. You're only going to affect the ones that are nearest. And even then, you may not affect all of them in the correct direction. So
Right.
it's going to be some are sent in, some are scattered away, some are just sped up, and it doesn't affect it in a meaningful way as far as sending things to the inner solar system.
So WA59 asks, are there any other hypotheses that explain these other comets besides the Oort cloud?
No.
Like there could there just be comets that are just passing through interstellar space? Or I mean, I guess they
There
can
could,
calculate the
but that wouldn't explain all of them.
because they're going to have a predictable or they're going to have an orbit they can calculate and say, no, that is in orbit around the sun.
Right, right, right.
Um, okay, so Mary Laura Griggs asks, I'll change her question a little bit here, but does dark matter or dark energy, so does dark matter cluster near or far away from the Oort cloud? Is there any relationship between dark matter and the Oort cloud? And I guess to further that question, could the Oort cloud be an explanation for dark matter?
So in terms of, we feel that our entire universe is filled with non-baryonics, so stuff that doesn't tend to interact via the electromagnetic force so that we can see it with light. Oort is baryonic matter, so it does not make up the primary constituency of dark matter. As near as we know, the amount of dark matter in our solar system is fairly constant. It's at a very low level, and much to everyone's consternation, we haven't been able to measure any effects from it within the size scale of the solar system.
That's a good question. So Hugo Nebula asks, could stellar perturbations cause more than one Oort cloud? So could you end up with multiple Oort clouds around
so that would be multiple shells?
Multiple shells, right?
And there's nothing to prevent there from being nested shells of material. Within our own solar system, we only need one to explain what we observe.
Right. Okay. And so but it's a continuum, right, of comets at various points along that thing. If you actually saw like comets that are either on this orbit or comets that come from that orbit, then you would start to think that maybe there is a shell. But because they just come from kind of all over the place in all directions,
and you have a limit on how big an Oort cloud can be before gravity no longer allows things to stay bound to our solar system. So the outermost edge of the Oort cloud is defined by where the gravity of the sun just isn't strong enough to hold on to things.
Paul Curtis asks, is there an estimation for the furthest extent of the Oort cloud? Theoretically, how close could the edge of the Oort cloud be to our nearest extrasolar Oort cloud? So I guess us and Alpha Centauri's Oort cloud, how much?
So it's about a quarter. It's about a quarter of the way out from us toward Alpha Centauri, and if you assume similar geometry, they'll have one a quarter of the way out to us as well. So that leaves 2 light years between them, I guess. In theory, assuming similar systems. Although I think that.
Uh-oh. I think we lost her. That might be the end of this episode of Astronomy Cast. We'll give her a second to get back in. But you can imagine the situation, right, where you've got these quite large clouds of Oort clouds around all these stars, and actually extending out this 0.8 of a light year in all directions. So actually, the amount of space out there that's not Oort cloud is a lot smaller than you would think. Let's see if there's any more questions here.
Sorry about that.
No problem. Okay, so Andrei Brovchenko asks, why does dark matter not clump in one point and stays in blobs in and around galaxies? Does it interact with itself?
So dark matter is what's called a non-collisional, non-baryonic material. So what this means is its cross-section is so small that it doesn't really ever collide, hardly at all. So in order to clump and bind up to form planets and things like that, you need things to be able to attach. So it doesn't do that. It doesn't have that chemical binding. Beyond that, it's such a low mass material that it clumps at huge scales, but at smaller scales it can't effectively pull itself together.
And as we've said, it has no cross section. So
Yeah.
you can throw a cloud of dark matter at another cloud of dark matter,
And they
and none
just
of it's going to
pass
bump
through.
together, just pass right through each other.
Yeah.
So whatever trajectory each individual particle of dark matter is on is the trajectory it's going to stay on, unless it gets changed by gravity. But it's not going to get changed by tidal forces or any kind of interaction with other objects. It's not going to get
Right.
bumped and collide and things like that, which is, when you think about the early solar system, all these little particles colliding together and building up into these, accreting together
Yeah.
to make boulders and eventually planets. You just can't get that with dark matter.
Right.
I've now, do you know anything about this? I've heard rumors that there's a big announcement on dark matter coming. Have you heard about this at all?
I tend to disregard those because I
Me
don't
too.
believe them.
Yeah, me too. But I've heard from, and I don't remember, and we'll be reporting on it, I think. I've
Okay.
heard that there's anyway,
A
I know that's
legitimate big release.
there's legitimate discoveries made in dark matter. So
Okay, cool.
you heard it here first, with no details and no confirmation. I have to remember where I heard it, but Tobitej says, would the James Webb Space Telescope be usable for observing the Oort Cloud?
It depends on the temperature. In theory, yes.
Really?
Yeah, because it's a big IR telescope, and IR is where these things should be the brightest. Now, the trick is getting time. The James Webb Space Telescope is such an expensive object. There's only one of it. You really need to have a good reason to be able to use it to observe things. And it's not a survey instrument. You're not going to go out and get night after night after night to survey a set region of the sky trying to find trying to find Oort Cloud objects. So that's a bit problematic. But if you have hints of something, it's certainly going to be excellent for follow-up. It might be a good way to, when we discover the next Sedna, to get even better imagery of it.
Patrick Festa asks a quick question. When you say 0.8 light years, do you mean diameter or radius? You're talking about radius, right?
Yeah.
50, and it's 50,000 astronomical units as well, is the other way to measure it. So
Yeah.
sun, 0.8 light year out, and 0.8 light year. So that's a big, it's 1.6 light years across, right?
Yeah.
That's big. Good. Well, I think we're kind of out of most of the questions here. One more. Time to Wonder 70 asks, did our oceans really arrive here from comets?
Yes.
Probably. Because
they arrived here from something that wasn't here originally.
Yes, but I know that we reported on this in Universe Today, that there was also sort of another theory that the planet could have picked up water that was formed in that inner part of the solar system as well. So
that doesn't make any sense. The inner part of the solar system got blasted dry by the sun.
I'll dig up the article for you.
I'm betting it's further out. It would have formed beyond
Possibly.
the asteroid belt.
Yeah, it was like in situ water formation could have contributed to the oceans on the Earth, in addition to comets. I'll dig it up for you. I'll dig it up. Okay. So here's one more. What? Okay, so here's one. So David Jacob asks, is global warming causing the Oort Cloud to destabilize?
No.
No. The global warming is only Earth, and it's only causing our temperature here on the planet to destabilize.
Causing the glaciers and the penguins to destabilize.
Yeah. It doesn't. Global warming doesn't reach off this planet at all. John Hughes, a bit off topic, but when will Mars be best visible?
Oh.
Stellarium. For starters,
Yeah.
You should install Stellarium on your computer, and it will tell you when every object is going to come up, and it's a wonderful piece of software. But I'm just
next fall sometime?
No, we're going to see it in. I'm trying to think last year. But it moves faster. But we see it kind of in late spring in Saturn. Mars and Saturn.
No, but closest approach.
No, just when it will be visible, not closest approach.
Okay, I thought he said best visible.
Well, he did say best visible, yeah.
See.
But it was start being visible.
It's when it's at opposition is when it's best visible.
All right, let's find out when Mars opposition is.
Mars oppositions, let's see. Whoa, big table of numbers.
Racia. 2012, we had one. 2014 in April.
Yeah.
but it won't be at opposition, but it will be somewhat visible. And I'm not sure when, because Mars moves pretty quickly. So with Saturn and Jupiter, we get used to it showing up at roughly the same time every year, but Mars is moving a little more quickly, so kind of can't count on it to be at the same place. We'll show it in the virtual star party when we see it. Now you've gone down the rabbit hole of.
Well, no, I'm having this. I'm looking at the same thing that you're looking at, and I'm trying to figure out why Mars doesn't have an opposition every single year, because it should. Because really, we go by it every single year. So I think we were looking at a Fubard table.
No, not. No, it's got a it's got a 2-year opposition period, which is when they always send because Earth and Mars are going at different rates, right? They're both moving around the sun.
Yeah, okay. I guess it's moving such that we wouldn't have to pass it every single year.
Because by the time we've completed, it is also completed in orbit.
Yeah, no, that's true. We do have to catch up to it. It's not like Jupiter that's moving so slowly that we go past it every year.
Yeah, but take Stellarium and do a search for Mars on Stellarium, and then just run the simulation fast forward, and it'll show you when Mars is going to look great from your point of view.
Yeah, and so it's looking like April 14th, 2014.
Yeah, and that's when it gets bright, but you can start to view it before then. So awesome. Okay, well I think we're done. Thank you very much, Pamela. Thanks everybody for watching us. We will see you. What's next?
Next is tomorrow with My Moon. We are going to be talking lunar science. I believe that's at 7 p.m. Central. I will be sending out an event announcement as soon as I get to my other computer.
And that's on Tuesday, a rare Tuesday event. Okay.
We're looking to move more and more things to Tuesday, so stay tuned.
Okay, great. All right, well, thanks, everybody. Thanks, Pamela, and we will see you all next time.
Sounds great. Talk to you later.
We'll find you a telescope to look through if that's where we are. So otherwise, we'll all just gape in awe at this gigantic model of the James Webb Space Telescope.
We'll have iPads with CosmoQuest on them, so you will be able to do science.
Yep, we'll get you to do some science, and then inside the big tent, there's going to be a gigantic wall that's going to have, like, I don't know what the plan is. They're going to have like big space stuff on the wall.
We're doing presentations. I'm giving 2 presentations each day. They're going to have astronaut John Grunsfeld, Nobel laureate John Mather, a bunch of other amazing folks. Sunday night they're going to be looking to break the world record for the number of people taking an astronomy lesson in the public at once. So yeah, lots of good things going down.
I wonder if there'll be a test at the end.
I don't know.
All right, cool. So are you ready to go? Are you ready to record?
I'm hoping. So this might be one of those more interesting episodes because there is a lag between the audio and video going on.
Are you seeing a lag from me or a lag?
It's caught up for you, but for a minute you had a 3-second lag between your audio and your video.
Okay.
We'll live. Yeah. We always do.
Yep. Yeah, it doesn't matter. It doesn't affect the recording, so. Just makes the YouTube video worse.
It looks more like the news reports where one person's in Afghanistan and it's going through satellite feeds.
Yeah, that's funny. Someone mentioned our
press record.
Are you ready to press record? Okay, all right.
You are frozen. You have stopped moving entirely. There we go. Now you're catching up.
Okay, I suspect it's your bandwidth.
Yeah.
Okay, all right. So have you pressed record yet? Ready? Are you there? Are you ready to press record?
I've pressed it. It's not doing anything.
There's your problem.
I'm here.
Okay, tell me when you...
But I have a whirly rainbow. Okay, now I'm recording. We're all good. We're recording.
Okay. There, and I'm pressed record too, and it's working just fine without a whirly rainbow. All right. Let me get my intro going here. Okay, here we go. Astronomy Cast, episode 292 for Monday, February 4th, 2013, the Oort Cloud. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest.org. Hey, Pamela, how you doing?
I'm doing well, Fraser. How are you doing?
Great. So I'm not sure if anyone's going to get this, but we're going to be at South by Southwest in Austin for the South by Southwest. All right. So that for a second, there's no way to make that smoother to switch from having the splash screen up to actually doing the recording. You just gotta
just commit.
Yeah. Yeah, absolutely. Great star party last night. That
I
was really,
thought so.
it was really good. We were in a silly mood, which is always important.
Isn't that always true as
I
well?
I think we could say that every episode of the virtual star party has a little bit of silliness in it. But there's some great objects, and the stupid moon, which we look beautiful, but
I'm
also
not sure
was.
that the moon actually has an intelligence quotient.
I wonder if we can destroy it. Can we destroy the moon? Because that would really help our astronomy. Yeah.
I think it would actually be rather bad for the surface of our planet.
But good for astronomy. So, and maybe if you gather together astronomers and put together a fund and see if we can destroy the moon. Um, why walk on the moon when you can destroy it? So, all right. So, for anyone who doesn't know what's going on here, it looks like the silliness is clearly carried over from last night. So, we're going to be doing a live episode of Astronomy Cast. That's where we record our long-running podcast, where we're going to be discussing today's topic is the Oort Cloud. And I know I'm going to get some emails from West Interactive exhibit with NASA, and we're going to be near the great big model of the James Webb Space Telescope from March 8th to the 10th. And so if you're going to be in Austin, by all means come by and say hi to us.
And we aren't going to be doing a meetup because our meetup is the NASA tent. So just come join us, no bracelet required, open
Yeah.
and free to everyone.
Yeah, we'll be there for 3 straight days. By all means, come by, say hi, shake our hands. Yeah. Awesome. Okay. Do we have any more announcements?
Don't think so.
No? Nothing interesting happening on CosmoQuest? Well, tons of interesting things happening on CosmoQuest, like completely rebuilding the forum and
Yes.
such. But yeah, the technical things. Okay, great. Well, then let's get going with the show. So the very outer reaches of the solar system is a region of space known as the Oort Cloud, which may extend as far as a light year from the sun. We only know about the Oort Cloud because that's where the long period comets come from, randomly falling into the inner solar system from time to time. So, Pamela, this is a funny thing where we've got an object, a structure, a thing in space that we actually have never seen, right? We can only just sense, detect, we have to presume that it's there, but we actually can't see it.
And it's really annoying because there's so many different
From people who can pronounce it properly, Oort Cloud. We're going to be recording the episode of the Oort Cloud, and then we're going to stick around for 15-20 minutes afterwards and answer any of your questions about space and astronomy. So we'll be getting that rolling right away. Now, did we have any announcements? I think the people who are watching this right now, just a reminder that we're going to be going to South by Southwest in Austin, Texas from March 7th till 11th, really the 8th, 9th, and 10th. And we're going to be hovering around the gigantic model of the James Webb Space Telescope, life-size models as big as a tennis court. And we're going to be doing virtual star parties, we're going to be doing a weekly space hangout, and we're going to be helping out with the telescopes and giving people a view to the night sky. So if you're going to be in the Austin area for South by Southwest, definitely look us up. Hopefully you'll recognize us there.
No bracelet required. Everyone is welcome at the NASA event.
Right, so you don't even need to pay any money to get into this stuff. Perfect. Yeah, because it's like $1,000 to go see the bands part, but
Yeah, I have no idea. So we're going to be there for South by Southwest Interactive.
yeah.
And we will be trapped in our tent down at Zilker Park, and we're going to be trapped by all the enthusiastic people who come to see us and come to learn science.
So definitely, if you recognize us, drop over, say hi, shake our hands. We'd be glad to see you and glad to